resistivity and resistance. Now, we introduced this concept of the current density, okay, this J vector. And basically, we can say that the current density, I don't know why we have a little dot here. I'll have to change that. That should be an equal sign. The current density is equal to the conductivity of the material times the electric field. And what that's just saying is you're going to get more charge flowing the more conductive the material is for a given amount of electric field. So for instance, silver is very conductive. So a small electric field created by a potential difference is going to move a lot of charge. If we have something that's less conductive, then the current density is going to be lower, meaning that for a particular wire, you're going to get less current through that. So we're going to talk about not so much conductivity, how good a material conducts the flow of charge. Rather, we're going to invert this and talk about resistivity, how much a particular material resists the flow of charge. So resistivity, which is this little row right here, is again the inverse of conductivity. So one way of measuring the resistivity of a particular material is if we apply an electric field across it, how much current density do we get? The more resistive the material is, the more electric field we need for a particular current density. Now again, current density and conductivity aren't as important for a lot of the things that we're going to do, especially for later chapters here. So we want to, again, get away from current density, talk about current, talk about resistivity, and then we're going to bring it back and finally talk about resistance and voltage. So, what makes something a good conductor? Well, low resistivity, high conductivity is typically found in materials that are metals. Metals are great conductors because the metallic bonds have free electrons moving within the material. So we look at the resistivity, 10 minus 8, really good for these types of materials. This actually is 10 to the minus 6 for nichrome, so it does drop off for some of these metal alloys. But great conductivity, very, very low resistivity. We get to the semiconductors where we're starting to talk about bonds that are somewhere in between being covalent and metallic. They're still technically covalent, but they do allow electrons to jump from place to place and holes to jump from place to place. So here, the resistivity has gone up significantly, many, many magnitudes, but it's still relatively low for carbon. Carbon's not metallic, obviously, but kind of has a semiconductor feel to it. Germanium is a semiconductor, and certainly silicon is a semiconductor. Once we get to the non-conductors, the insulators, the resistivity is very, very high. We don't have any free charges to move, so really you're going to need an extreme electric field to get any flow of charge. Silver. Why don't we use silver for electric wire? Well, you probably know the answer to that. It's many times more expensive than copper. Although copper, the price of copper has gone up quite a bit, whereas silver has sort of stayed the same. It's more reactive than copper, so we don't like to use silver because it'll oxidize, making electrical contacts a little more difficult. So we get 7% more conductivity than copper, and like copper is very ductile, but just 7% isn't enough to overcome the expense and also the oxide problems. So we don't usually use silver for electrical connections. Again, copper is used for most electrical wiring, most electrical transmission. It's the second most conductive metal that we have. Very ductile, which means we can draw it out into wire very, very easily. The cons are it is becoming relatively expensive just because it is such a good material for the purpose of wiring. So low resistivity, high conductivity. Remember, these are reciprocals of one another. The conductivity and resistivity are reciprocals. Gold. Okay, gold is one of those materials that is really, really expensive, but we can use extremely sparingly because gold, we can gold plate things. We can put, just atoms thick on a material and coat it and protect it. It's the third most conductive metal, and because it has a very low chemical reactivity, when we create connections with gold-plated connectors, we don't have to worry about them oxidizing. You get an oxidizing layer on metal, and it's going to be hard to send electricity through that oxide layer. It's going to cause more resistance. So here you actually the backside of a high-end microprocessor, and all the connections are gold coated, and that ensures that when it's placed into the microprocessor socket, that you've got a good electrical connection between everything. Okay, so again, pros: very low chemical reactivity. Gold is a noble metal; it doesn't really react with much of anything. I think the only thing I can think that it even reacts with is aqua regia, which is nitric and hydrochloric acid. But because of its expense, we typically only use it to create very thin coatings. Aluminum. Aluminum is used for large electrical cables, for large electrical transmission. The reason for it is it's the fourth most conductive metal. It's light. It's inexpensive. I would say the problem is you don't want to use it in small wires. It oxidizes, it's reactive, and an oxide layer can make a very difficult connection when you're dealing with a small connector. When you've got big lugs on single aught and double aught wire, which is the gauge of this, you can get around some of these oxide problems. But we also have the problem that it breaks easily. It fractures, being a softer metal, much more easily than something like copper. So inside the home, most of your wiring is going to be an alloy of copper. Outside the home, the service to the home, you'll see aluminum used quite a bit, and also on the transmission lines, we use aluminum. Nice and light, and very strong for its own mass. And as long as we make good connections with it, we're careful with the way we make connections, we can get away from some of the oxide problems that we have. Tungsten, very specialized metal. We use it in heating elements and lamp filaments. It has a fairly high conductivity. It's a difficult metal to work with because of its brittle nature. It's actually a very strong metal too. But the main thing that we like about tungsten is its high melting point. You can heat it up to 2,000 degrees Celsius, and it's still going to have a fairly high strength to it. So tungsten, we'll see, it's been used for years in the filaments for incandescent lights. It's actually used in the starter filaments for fluorescent lights also. And of course, tungsten is used in electric ovens, where you're going to a very, very high temperature, like ceramic ovens is what I'm talking about. You can use tungsten in the heating elements. Speaking of heating elements, nichrome wire, which is an alloy of nickel and chromium. It's actually an alloy of nickel, usually other materials. Sometimes they'll put iron in there. Sometimes they'll put vanadium in there, I think. I might be wrong on that. But this alloy of nickel and chromium, when it's heated to a very high temperature, it actually forms a layer of chromium oxide. And this is going to protect the wire from oxidizing. When we heat metals up, they react with the air much more. And because of this reaction, if you're using other metals at very, very high temperatures, they're going to fail fairly quickly. When we heat this wire up, it forms a protective layer of chromium oxide on the outside. The chromium makes it slightly toxic, so we've got to be careful there. What we'll often see is this wire will be used by itself, as you see in this picture right here, to generate heat from electricity, or they'll actually cover it with a ceramic coating. And those are typically the heating elements that you see in electric stoves, electric ovens, electric heaters, space heaters, things like that. Very, very good material to use as a heating element when you're delivering a tremendous amount of electrical power and converting that into thermal energy. So these are all metals. all very high conductivity, okay, low resistivity, and because of their low resistivity, we can send a lot of electricity through them without a lot of loss. You know, the interesting thing is we actually are trying to lose the electrical energy when we're sending the electricity through nichrome, and it does have a higher resistivity than some of the others, at about 10 to the minus 6 ohm meters. We go back to copper, which is the most common element used for electrical wiring, and you can see its resistivity is 10 to the minus 8. So nichrome is about 100 times more resistive than our copper and some of the copper alloys. In any case, here's even an expanded view. Again, we've got all the metals. Here's our nichrome right there, being one of the more resistive metals. Here's our silver, being the least resistive of the metals. Then we transition to some of the semiconductors. Seawater is resistive, but not resistive enough to prevent the propagation of electricity when we're swimming. So that's why, you don't want to be swimming during a lightning storm. And even drinking water has enough conductivity that you can easily become shocked when exposed to a voltage. So, certainly won't want to be careful. What's interesting, though, is if you look at deionized water, pure water, actually has a very high resistance. That's notable to see that the electrolytes really change the electrical properties of water, even at very, very low concentrations. And of course, we have some of the highest resistant material, glass. Ceramics are very similar in resistivity to glass. Hard rubber, fused quartz, polyethyl, oh gosh, I can't remember that. PET. I'll have to get back to you on that. Of course, Teflon is tetrafluoro. Okay, so it's been a while since I've had organic chemistry, but Teflon is an excellent insulator. We talked about the use of Teflon in dielectric capacitors, but we also talked about it because of its low friction too, but different materials that we can use. So metals, great conductors, low resistivity, high conductivity. Insulators, just the opposite. It's interesting to note also that the temperature actually changes with resistance. These previous resistivities were at 20 degrees Celsius. As we heat a metal up, we're making the electrons go faster and faster. They collide more, and this is going to contribute to more and more resistance. So as we heat the metal, resistivity goes up, and it's actually easy to calculate the change in resistance, because when we look at the resistivity compared to what it is, usually it's some set amount, usually rho naught represents 20 degrees Celsius, or the resistivity of 20 degrees Celsius. It goes by 1 plus alpha. Alpha is the temperature constant, not of thermal expansion, but of resistivity. It's the temperature constant for resistivity. And this is delta T, the difference in temperature between what you're measuring and what it would have been at 20 degrees Celsius. So going back again, here are temperature coefficients. For metals, it's positive, which means they become more resistive as you heat them up. Semiconductors actually become less resistive. And that's because as we heat them, we're making the bonds, we're agitating the bonds more and more. It's more likely that we're going to free electrons to carry charge. With metals, the electrons are already free, so all we're doing is increasing their collisions, and that's why the resistance goes up. So this is the equation that we use to calculate resistivity given some resistance at 20 degrees. Again, you need to look up the temperature coefficient and just know what your temperature is, see what that is. Later on, we'll talk about how resistance is related to resistivity, length, and cross-sectional area of a wire. Resistance is measured in ohms. So what determines your resistance for a particular conductor is what material you're using, okay? What temperature it's at, because this rho, again, has a temperature dependence. It's not great. It's mainly dependent on the material, but there is a slight temperature dependence. Longer wires, they resist the flow of electricity much more than shorter wires. And cross-sectional area, just like you can send more water through a bigger pipe, fatter wire,